So this is a paper that's not directly about producing green hydrogen, but showing a way to enhance the performance of metal oxides, which are used for thermochemical water and carbon dioxide splitting. And the paper basically reports on a new pathway to enhancing this performance by doing oxidations at high pressures, and shows that using solar energy as well, one can use this approach of oxidation at higher pressures to achieve the more efficient and more complete splitting of water and carbon dioxide, which can then produce green hydrogen, of course, and also syngases. Okay, so here is kind of a the graphical abstract. So here is thermal energy being envisioned to feed into metal oxide framework. So you are looking at oxidation and reduction. So elevating total pressure of the equimolar oxidation step above 1 bar. So here it is greater than 1 bar, and here is a less than equal to 1 bar, showing reduction and oxidation. So this is oxidation and this is reduction reaction. Elevating the total pressure of the equimolar oxidation step above 1 bar improves reaction kinetics, increases the extent of the reaction, so more complete, enables more efficient solar to fuel conversion, energy conversion. Okay, so you are going from 1 hour delta MOX to 1 hour delta MOX minus delta. So you are removing half of oxygen here, and you are removing you are splitting water into H2 here. So the two-step thermochemical processes for the dissociation of H2O and or CO2 via solar heat have historically performed the oxidation or fuel producing step at ambient pressure, and as a result, in practice, the work required for product compression is significant. So when you have H2 coming out and the product that is being oxidized is compressed, and you're putting in a lot of work by implementing oxidation itself at elevated pressure, as first demonstrated here. Not only can such losses be mitigated, but the performance of the reaction can also be improved. Ultimately, this study introduces oxidant pressure, a new dimension, into the thermodynamic and kinetic considerations of material selection and process design. Okay, so what are the highlights? The effect of total pressure on thermochemical H2O and CO2 splitting is evaluated. As pressure increases, the rate and extent of the equimolar oxidation step increases. So you can go and read the various reactions that are detailed in the paper, which obviously I'm not covering here. Materials that possess moderate reduction enthalpies show much greater improvement. So we'll see one abundantly available material for making this feasible at scale. Processes that adopt such pressure swing are capable of much higher efficiencies. Okay. In a summary, the thermochemical dissociation of water and or carbon dioxide over a reduced metal oxide has long been thought to be independent of total pressure, as the number of moles of gaseous reactants like H2O and CO2 and gaseous products such as H2 and or CO is then used to make syngas, is equal. Okay, the number of moles of gaseous reactants and gaseous products is equal. In this study, however, through careful experimentation, we conclusively demonstrate that in an open system where product gases are swept away from the reaction site, operating at elevated pressures improves both the equilibrium extent and the rate of the aforementioned equimolar oxidation reaction. These findings have important implications for the viability of commercial systems, as the discovery of a temperature-dependent technique for increasing reactant conversion not only enables the use of more earth-abundant materials, but may also finally facilitate the development of a process for the production of green hydrogen or syngas that's both practical and efficient. What are the scales? So context and scale. the widespread adoption of electrolytic processes for the large-scale production of green hydrogen or syngas, fuels essential for the decarbonization of industries not suitable for electrification, such as long-haul transportation, remains challenged by the need for scarce materials, significant growth in manufacturing, and a ubiquitous supply of low-cost renewable electricity. Solar-driven chemical looping technologies, on the other hand, offer a readily scalable alternative for the direct conversion of both H2O and CO2. However, despite numerous field demonstrations, a commercially viable efficiency has yet to be reported, a consequence of a perceived necessity that process steps must be performed at separate temperatures. In this study, we show that with select materials, example earth-abundant iron illuminates, elevating oxidant pressure offsets the need for such large temperature swings, thus paving the way for the emergence of an efficient yet practical approach for solar to fuel conversion. Okay, so keeping that brief intro, let's read what the conclusion is. In conclusion, two-step thermochemical process for splitting water and or carbon dioxide have thus far relied on large temperature swings to improve the thermodynamic driving force for oxidation and thereby enable higher conversion. In practice, however, doing so has resulted in, among other issues, inefficient operation as a viable approach for recovering the sensible heat rejected during the cooling continues to remain elusive. Okay, so there are ideas on how to use high temperature conversions but then recover the sensible heat rejected during cooling, but this latter part has not been very effective to justify the energy used for these temperature swings. Thus, although others have prioritized complex computational efforts aimed at discovering materials that minimize the difference in temperature at which each reaction proceeds spontaneously, we have developed a more general methodological solution, one that leverages the parameter of total pressure to circumvent the constraints of Le Chatelier's principle and enhance cycle performance. Le Chatelier's principle is basically about how reactions move in different directions based on perturbation of reactants, pressure, temperature, etc. By implementing the oxidation step at elevated pressures, not only is the work required for downstream product compression reduced, but the equilibrium extent and rate of the equimolar reaction can be improved, provided that the considered reactor represents an open system, so the product is taken away. And secondly, the redox candidate exhibits sufficient deviations from its fully oxidized state over relevant range of temperatures and oxygen partial pressures. In general, the latter requires that the candidate possesses a moderate reduction enthalpy, i.e. below 400 kilojoules per mole of oxygen. As a result, modes recognized for their simplicity, namely isothermal or near isothermal operation, are likely to become more competitive as with proper active material selection, inefficiencies associated with insufficient reactant conversion may now be alleviated by simply elevating oxidant pressure. So this is a new dimension that they have discovered to help these shortcomings or drawbacks of the older ways. We anticipate that such insights, when coupled with low-cost iron illuminate-based materials capable of isothermally outperforming conventional approaches, will lead to the long-awaited emergence of a new paradigm for highly efficient yet practical solar to fuel conversion. So this is not touting some new technology and claiming to have produced large amounts of hydrogen or syngas, but it is saying there is a way in which to do these using renewable energy to make the whole process efficient and more productive in terms of conversion of reactants to the products we are seeking, like CO or H2. Okay, all right. that's a short introduction, but obviously you can follow up if you're interested in further details.